Great. So next talk of the session's by Chelsea. She's going to tell us about on the adaptive security of key unique threshold signatures.
All right. Yeah, so thank you all so much for having me. Today I'm going to be talking about adaptive security and a class of threshold signature that we call key unique. And this is joint work with my longtime co-authors, Elizabeth Kreitz and Mary Maller. And yeah, I just want to say thank you to the organizers. And it's
Excuse me, you can go back to that.
Okay. All right. There we go. Good. Yeah, and I just want to say it's a pleasure to be here talking about adaptive security, especially with so many people here who have published work on threshold signatures and adaptive security. So yeah, so thank you so much for having me. Okay, so many of you probably are familiar with threshold signatures, but for those of you who are not, I'll review them very quickly. So we're talking about a special case of a multi-party computation for threshold signatures. And what we have is we have one public key, which represents a set of signers, and a secret key, which is partitioned among a set of signers. And we really talk about these schemes from a T out of N perspective, where T represents the threshold, so the number of parties that are required to participate in signing, and N being the total number of parties. So here I'm showing you a 2 out of 3 example, where 2 parties would be required to sign out of the 3 total parties. And generally we say the scheme is secure up to T-1 corruptions. So in our example here, 1 party could be corrupted, and we would say that the scheme still is secure. And key generation can be done in one of 2 ways. So it can be done via what we call a trusted dealer, where you would have one dealer which generates all of the key material for the whole set of parties. Or it can also be done by what we call a distributed key generation protocol. And yeah, so the reason why these schemes are interesting in practice is because signing can be done without revealing secret keys to other parties. So you have a distribution of trust. And what's exciting about threshold signatures is that we are seeing them used in practice. Generally, we're seeing them used within cryptocurrency wallets, which I'll talk a little bit more. But we see them used in exchanges, and then one setting that we hope to see threshold signatures being used in is something like certificate authorities or trust authorities. So basically, if you're issuing something like a web certificate, hopefully in the future we start to see threshold signatures being used in this context. And one kind of critical moment in the history of threshold signatures in the cryptocurrency space was what happened with an exchange called Mt. Gox. So Mt. Gox held a bunch of users' funds. All of these funds were within what we call a hot wallet, so a wallet that was connected to the internet. And essentially, hackers were able to infiltrate the exchange, steal the keys, and therefore steal users' funds. So I think in the history of threshold signatures, this sort of galvanized the need to have distribution of trust when safeguarding secret signing keys. And yeah, so within that interest, we are starting to see standards efforts as well. So there's an open call for NIST for the standardization of multi-party threshold signature schemes. So this is an ongoing effort. Okay, so I've been using the word security a little loosely. So there's several notions of security we can think about. And one of the first notions that we can think about is this notion that we call static security. So basically, static unforgeability. So for this, you can think about it in a very similar way as unforgeability for a single party signature scheme. But here we have an adversary that can participate in the signing protocol. And what it does at the beginning of the experiment is it chooses a set of parties that it wants to corrupt. And it receives the secret key shares for all of the parties, as well as public key material. So kind of at the beginning of time, the adversary says, I want to corrupt this set of parties, and it receives the secret key material for those parties. And then it can query honest signers of its choosing, and the adversary representing these corrupt parties can participate in the signing protocol as it wishes. And the win condition is similar to a single party signature, where if it can produce a forgery on a message that was not queried to an honest signer, we say that the adversary wins the experiment. Okay. For adaptive unforgeability, it's a little bit different. So in this setting, the adversary is given a corruption oracle, And instead of declaring at the beginning of time which parties it wants to corrupt, it can adaptively corrupt the parties that it wishes on the fly. So it could, let's say, query for on a signer 1, and then it could corrupt signer 1. Okay? So basically, throughout the entire experiment, the adversary can corrupt parties of its choosing, and that's why we call it adaptive unforgeability. So this notion of security is interesting because it does model what we would think a real-world adversary would do, right? So a real-world adversary, we wouldn't expect to declare at the beginning of time which parties it wants to corrupt. We would expect that it would do something more along these lines. So yeah, so in theory, we would want to sort of target this notion of security. But when we write proofs for this notion of security, there's a few trade-offs. And really, like, the overarching trade-off is that writing proofs becomes more complicated and a little bit more complex. So when you write a proof for this notion of security, you have to simulate the secret key shares for the corrupt parties, but also things like signing state. So for example, the adversary could query the first round of signing for all of the parties, and then it would corrupt those parties, and so you have to simulate state throughout the protocol. So that's why these proofs tend to be a little bit more involved, and why they aren't necessarily the first thing that we reach for when we prove unforgeability for threshold signatures. Okay, I think it's important to point out, I mean, it's a little bit obvious, but you can essentially get trivial adaptive unforgeability from guessing. So what you could do is, like, given essentially a static reduction, the reduction could guess the parties that the adversary wishes to corrupt, and then it could just simply abort if the adversary decides to corrupt a party that's not in that set. Okay? Yeah, so this might be fine for a small set of parties, but the tightness loss grows as the number of parties grows in the corruption threshold. And yeah, so I think for a long time, and sort of when you talk about this with people, there was always sort of this implicit argument that we could get trivial adaptive unforgeability from this guessing argument. And there was always a question of whether or not it was important to get improved bounds for adaptive unforgeability. So there's sort of this consideration of, okay, we can at least do this well. Is it important to have tighter bounds? And yeah, that's, I think, a very important question to consider, and something that I think we should keep in mind for the rest of this talk is, like, is having non-trivial adaptive security actually meaningful? And I think, I don't know, like, as someone who's published in this area, I am myself not quite so convinced. So this isn't like me standing here saying, like, this is the most important notion of security and we should aim for that above all other things. I think this is a very nuanced question, and as people working on both theory and practice, this is something we really should think about and consider, like, what does this notion of security actually mean? And I guess, like, for my personal opinion, I don't think adaptive security maybe, like, should be chosen over implementation considerations like performance or simplicity, but that could change depending on our analysis. So this is, like, my personal opinion, and others might have different opinions, but I think it's an open question of where does the trade-off between implementation considerations and adaptive security? And I think there's actually a lot that we can learn in this area, and there's a lot of things that we should study.
If a protocol is not adaptively secure, then you introduce an adaptive adversary into the protocol, can they generate a forgery, or do they just cause that no signatures can be created? Those are two different cases, and maybe an answer to that would somewhat help shape the answer that you're debating with, which I think is important.
Yeah, is there, like, a meaningful separation between the two?
Is there a meaningful attack? If the protocol is non-adaptive and an adaptive adversary is in the system, can they create a forgery, or can they just foil the signature from being created?
That is an important question.
And what is the answer?
I think
It
we.
was a question.
Oh, the
Yeah.
question is, do we know of any where like there is that kind of meaningful
Yes.
separation?
Yes.
So there is a new paper. So there's actually 2 papers at Crypto that address this question. So I will refer to those 2 papers. But basically, there's 2 papers at Crypto that look at what we believe to be an inefficient attack in the adaptive setting that is not possible in the static setting.
The attack is forging?
Yes, it's a forgery attack, and we believe. I'll get into it later in the talk a little bit, or I won't talk about the attack. I will refer to the papers.
When you
But-
say inefficient, sorry, is there a characterization of the inefficient quickly?
It's an assumption, so we need cryptanalysis to actually decide if we think it's inefficient or not.
Okay, but
So-
it's an assumption that's not necessarily needed for static.
Correct. Yeah.
But
and
using
I'll-
complexity leveraging, you can always do it, right? So
Yeah.
the loss can at most be it's an improvement over what the complexity leveraging attack would be.
We're not sure. Yeah, so that's why we need cryptanalysis. So I'll at least show where this is. I have a case study where I'll give a case study. I won't go into the attack. I'll just refer to the papers. But that's why at least I say like we do need more cryptanalysis to see if there are maybe potentially more attacks. Maybe this attack is efficient. I don't think it is, but yeah. So I'll get a little bit more into that, but not completely.
So we do not even have contrived examples of selectively secure signatures or threshold signatures which are provably not adaptively secure. Even contrived counterexamples do not exist yet.
I'm not sure. Yeah,
Choose
the
the random
papers true.
community,
Yeah.
announce it, and use this community as the decided. That's trivial. For example.
Yeah, yeah, so exactly. Yeah, so the question is, are there like meaningful, non-trivial examples? Okay, yes, exactly. So that's a research question we're interested in asking. And especially like what security assumptions are also required. Okay, so I want to give you a case study that sort of separates, or shows this kind of separation between static and adaptive. And for this case study, I'm going to highlight a scheme called Frost that I'm a co-author of, but that many other people have also studied the security of. So yeah, so basically Frost is a true-round threshold Schnorr signature. And the way the protocol works is you have parties choose 2 nonces at random, and then they will generate 2 commitments to those nonces, and they'll send those commitments to all the other parties and receive commitments back from all the parties. So this is the first round. Then each party will just hash the transcript from the first round, so just take everything and hash it. And then we generate the commitment as just the combination of the group commitment as the combination of the 2 commitments, tweaked with essentially the transcript from the first round. Okay, so you basically use the first round as a tweak to this commitment. The challenge is exactly the same as done in plain Schnorr. And then the response, you just use these 2 nonces along with this tweak. And then here you have the challenge and this SK1 lambda 1. This is the secret key for the secret key share for party 1, and the lambda 1 is the Lagrange coefficient. Okay, so just as a reminder, basically you can do polynomial interpolation from Shamir secret shares. So you can basically interpolate to any other point. So here the secret key is just the interpolation of these secret key shares. And then our combine is taking all of the responses and summing them. And then basically you can verify with respect to the plain Schnorr verification algorithm. Okay, so yeah, so this is Frost. Yeah, so the reason why we like Frost in practice is because the first round is message independent. It's a pretty simple protocol, and it's backwards compatible to Schnorr. Yeah, so I'm showing this scheme to you because it is like used quite widely, and there's the internet informational draft for Frost. So it's something that people are adopting in practice. It's simple and it's efficient. So it's interesting as a case study because So we recently put out, this is one of the papers that's been accepted to crypto, but we were able to prove the adaptive security of Frost. And we're able to kind of show a separation between the assumptions that are needed for static security and the assumptions that are needed for adaptive. So in the static setting, we can prove the security of Frost under what we call the algebraic one more discrete logarithm assumption. So this is an interactive assumption. And then we're also able to prove adaptive security up to t/2 corruptions in the same model. Okay? But then when we go to prove adaptive security up to t corruptions, where the threshold is t+1, we need additional assumptions. So in this case, we needed the algebraic group model, and then this new assumption, which we call the low-dimensional vector representation assumption. Yeah, again, I'm not going to go into the technicalities of this, but this is a new assumption, and it's something we're hoping, yeah, we hope others look at this and think that it's, yeah, solving this is not efficient.
The AOMDL is implied by AGM.
I guess that is true. Yeah, I'm not totally sure. Is that a statement or a question?
Yeah, it's a statement.
Oh, it's a statement, yeah. Okay. Oh, I think maybe just to be clear. Yeah, just to be clear. Okay. Yeah, so I think this is interesting. So I guess, yeah, so some research questions that like inspired this work was that like, can we do any better than this? And like, is this, so this is something we thought about in this impossibility result paper. But I think the broader question to the community is like, is this separation meaningful? And so that's a broader and deeper question that I hope us as the community can think about. Okay, so along with Frost, there's been a lot of adaptively secure schemes that have been published. This is just within maybe the last year and a half. So like another research question we can think about is like, how can we actually classify these schemes? And we see that a lot of these schemes have like quite varied assumptions that they're being proven under. So yeah, so something else we thought about is like, yeah, again, which assumptions are inherent and why? So like what is like something deeper that's going on within all of these adaptively secure schemes? Okay, so yeah, so just for our results, just to kind of give a high level of what we did. So what we do is we start by describing what we call a Q-unique threshold signature, and I will describe what that is. And then we give two impossibility results. So the first impossibility result is we show that under any Q-unique threshold signature, you can't prove that it's adaptively secure under under T corruptions with respect to non-interactive computational assumptions. And I'll give a definition of what that is. So that's our first result, and then our second result is for Schnorr threshold signatures in particular, mainly because it's kind of a hot topic, and it's something that we'd published on before. But yeah, so basically our second impossibility result shows that even if you assume an interactive assumption, you can't have a Q-unique Schnorr threshold signature with rewinding. So basically your reduction needs to be a straight line. And so this sort of speaks to the need when we proved the adaptive security of Frost, why we needed the AGM, because our reduction is straight line. So I guess it does somewhat validate the assumptions that we proved Frost under. Yeah.
And does this results have any implication for ECDSA type signatures?
The first result does, yes. The second result doesn't, but.
So it also implies, your first result also implies it for ECDSA?
This result is for threshold signatures in general. For Q-unique threshold signatures as we define it, and Q-unique does apply to ECDSA and BLS. Mm-hmm. Okay, so I just want to caveat this for some of you who have worked in adaptive security. I just want to give a caveat that maybe the results that I'm about to show are maybe not so surprising. So if you're thinking this, it's probably because you've published in this area. But But I think, like, regardless, what these results do, I hope, is frame the research landscape and sort of the implications and trade-offs. So yeah, I think it'll be fun, and I just want to acknowledge that many of you have published in this area. So we'll we'll see how this goes. Okay, so just a little bit of background. So I'm talking about non-interactive computational assumptions. And really what I mean by that is just where you have a challenger that gives an instance. So it gives a challenge to some adversary. The adversary will output what it thinks the solution is. And then there's an efficient verification algorithm that checks if the solution is correct. So really here, we're just giving an abstraction to many of the computational assumptions that we know and love, like DL, CDH, and then some of the pairing-like assumptions as well. Okay, so yeah, so this is just a generalization of many of these computational assumptions. And then I want to remind all of us what a meta-reduction is. So we use meta-reductions to prove our impossibility result. So yeah, so basically with a meta-reduction, what we do is we assume a reduction exists, and we treat the reduction as a black box. And then we define one particular adversary, and this particular adversary could be unbounded. But then we define an efficient meta-reduction, which simulates this adversary, and then it uses the reduction as an algorithm to solve some assumption. So basically, we're doing a proof by contradiction. So we say, if this assumption is hard, then such a reduction should not exist. Okay? So it's basically a proof by contradiction. Okay, so let's go into the definition for key uniqueness. So I want to remind us, like, when we say key generation for threshold signatures, what does this mean? So essentially, we have a keygen algorithm that will output a set of n secret key shares along with an associated identifier, and then the public key shares for each participant along with a public key. Okay, so this is just the overall algorithm. So when we say that a scheme is key unique, we say that there's two particular properties associated with that scheme. One of a unique correspondence, and second for efficient verification. So for the first property, basically what we mean is that the public keys and shares basically you can generate the public keys using an injective map F. So given any secret key, you have some injective map F, which will generate the public key. Okay? And then we just give these labels to sort of distinguish whether or not you're generating the group public key or if you're generating the public key shares. And then for the second property, for efficient verification, we basically say that there is a verification algorithm that can check if the public keys are well-formed. So we say that if this algorithm exists, and if it says that these keys are valid, then given secret key shares from the set of parties, you can recover the secret key. Okay?
I think I missed the point. So there's only one representation of shares that corresponds to the secret key that corresponds to the public key?
Yes.
This means that proactive techniques are not, you cannot apply proactiveness in this setting.
That's a good question. Because you can change. In proactive, though, the secret key share does change.
Yes, there have to be multiple representation of the same secret key. So
Of the
that's why I
same-
asked
Yeah.
if it's a set of shares is the only representation for this.
We're saying for each secret key, there exists one public key.
That, of course.
Yeah, and then for each secret key share, there exists one public key share. So the
Okay.
secret key shares can change.
Okay.
And the
So it's not that the set of shares
can't change. It's just
not
saying that there's a
change.
map.
Once you've done the first thing and you've fixed the public key, so there is some key SK. You can have various representations via shares of that key SK.
Yes. Yeah. I'll give some examples of what I mean by Q-unique as well. So I have 3 examples. Okay, yeah, so for this, I'm just saying that there's an efficient verification algorithm. If this verify algorithm outputs 1, then you can recover the secret key. Okay, I do not have a lot of time, so I'm gonna maybe just focus on these examples. Yeah, I'll just focus on the examples. Okay, so the first example I think is kind of obvious. So basically here, we just have a Shamir secret share of the secret key. And then your public key shares are just the generator raised to the secret key. So this would encompass things like proactive security, where you can change the secret key share, and the public key shares would also change. Yeah, the reason why I highlight this example, so it is Q-unique, and it's used by many, many schemes in the literature. Okay? So yeah, so this is a Q-unique. Any scheme that uses this for their key material would be considered Q-unique. A scheme that would not be Q-unique is you, again, do Shamir secret sharing in the same way. But here, you would just generate the public key, and you would not generate public key shares. So the public key shares would remain secret. And then the parties would just get their respective share and the public key. They would not get the public key shares. So this is not...
Going back to my question, so now you're saying that in that scheme, there is a public key share that's associated with the share, with SI, which let's say in a discrete log simple one, it's just going to be G to the SI, so that you can do some proofs later that you're giving proper shares of signatures. But that means that if you want to keep all those PKI fixed, then there really is no other sharing that would fit. It's not that you'd be able to proactivize. If you would need to proactivize, you'd also need to proactivize the public key shares.
Yeah, I would love to discuss. Yeah, just in the interest of time.
Sure.
Yeah, I would love to discuss after. But yeah, so the reason why I want to show this example is, so this was employed by an adaptively secure scheme quite recently. They proved adaptive security of both Schnorr signatures and Lattice signatures. And it's quite cheap, right? Like you just don't output the public key shares, and then you can prove adaptive security. So this would be considered a non-Q-unique scheme. Okay. And then, but the trade-off with the scheme is you don't have what we call efficient identifiable abort. So if you don't have the public key shares, it's very hard to tell if someone were to output an invalid signature. Basically, is that you can't verify the correctness of that signature share. Okay, and then the third example I want to highlight of a non-Q-unique scheme is one that uses Pedersen commitments. So this has been used quite extensively in the literature. But basically, here, your public key share would just be the Pedersen commitment to a secret key share associated with the secret key, and then something like a sharing of the value 0. So yeah, so strategies like this have been used in the literature, and this is considered a non-Q-unique scheme. Okay. I have 2 minutes, so yeah, so I'm just going to re-highlight our results. So yeah, so basically what I did is I showed you key uniqueness and the properties that achieve key uniqueness, and I gave you some examples. And yes, so with our impossibility result, we show that you can't, if your scheme is key unique, you can't prove it adaptively secure under non-interactive computational assumptions with improved tightness than the trivial case. So just, yeah. So I guess like just to show you some schemes that this does apply to, so it applies to things like threshold BLS, ECDSA, and Schnorr, all which use this kind of key-unique approach. But then there's schemes that use a non-key-unique approach, and so it doesn't apply. Okay, and then, yeah, I'll just skip the second result, but it applies just to threshold Schnorr. Okay, so overall takeaways. So we've thought about adaptive security for a long time. It does model a real-world adversary a little bit more closely, and so that is something we would want to do in our proofs of security. But proving adaptive security under standard assumptions can be challenging. And basically what we do is we try to frame what assumptions are necessary given the structure of the scheme and how key generation is done. And I just want to point out that we do think that more cryptanalysis is needed, especially in the case like Frost, where we show this sort of separation between adaptive and static security and the assumptions that are required. Okay. And that's exactly at 30 minutes.
And maybe in the interest of time, let's take the remaining questions offline. Stay, Chelsea.